Everyone, welcome to the first session of the day. My name is Itai Dinur. The session is on hash function cryptanalysis. We're going to have three papers presented. The first paper is called Meet in the Middle Preimage Attacks on Sponge-Based Hashing. It is a paper by Lingyu Qin, Jialiang Hu, Xiaowang Dong, Hailun Yan, and Xiaoyun Wang. And Hailun is going to give the talk.
Thanks for the introduction. Good morning, everyone. My name is Hailun. In this talk, I will present our work on Meet in the Middle Preimage attacks on sponge hash functions. So this talk is divided into 4 parts. In the first part, I will briefly review the Meet in the Middle attack, especially the attack on hash functions. So Meet in the Middle attack is a generic technique for symmetric key cryptanalysis, which was first proposed by Diffie and Hellman in the year 1977. The main idea of Meet in the Middle attack is actually it divides the whole space into 2 parts, and we find collisions between them. So it's actually an efficient way to exhaustively search a space based on the bursty attack. A typical example of the application is the Meet in the Middle attack on block ciphers with double encryption. In the past decades, the Meet in the Middle attack has been widely applied to the cryptanalysis of both block ciphers and hash functions, and between some of which have been broken, like MD4, MD5, and so on. And in the meantime, various techniques have been proposed to improve the framework of Meet in the Middle attack. And there are also some automatic tools. I don't think I have time to introduce the related works. Please refer to the papers if you are interested in it. So let's look further at the Meet in the Middle attack on hash functions. Currently, most Meet in the Middle attack on hash functions are targeting the so-called Markov-Damgard construction. So in the Markov-Damgard construction, the compression function F is usually built by a block cipher via some hashing mode, which usually use a feed-forward mechanism. So it is a closed computation path. With this closed computation path, we can deploy the so-called splice and cut Meet in the Middle attacks. So first, we cut the compression function into 2 chunks at certain internal runs, and then one chunk is computed forward, and the other chunk is computed backward, and finally, both chunks will arrive at the same common run. And we can check a match here. Note that the forward chunk is actually computed across the first several runs and the last several runs via the feed-forward mechanism of the hashing mode. So in a higher level, the splice and cut Meet in the Middle can be divided into 3 configurations. The first one is the chunk separation. So we need to give the initial structure and the matching points. The second one is to select 2 neutral sets colored by blue and red, which determines the degree of the freedom of each chunk. The third one is to give a relation used for partial matching, which determines the filtering ability, also named as the degree of matching. Then it's natural a natural question is that, does it still work when it comes to the sponge hash functions? Let's see. For sponge hash functions, if we start similarly from some internal runs in the middle, we have to satisfy not only the H-bit target in the forward computation path, but also to satisfy the C-bit capacity value in the backward computation path, which means we have to search a space of 2 to the H plus C to find the preimage of the given target. Considering the time complexity of the exhaustive search is 2 to the h, it may not be a good idea. So we prefer to searching for a more compact space. So in the second part, I will show you our new framework of meet-in-the-middle attack on sponge-based hashing, and I will also give the automatic tools. This is the framework of our meet-in-the-middle attack. So in this framework, we choose to start from the R bit read part, and all the computation passes are forward. If R is larger than H, then H bit subspace of the read part is enough to find the preimage of the given target. Like the previous meet-in-the-middle attack, we also need 3 configurations. We need to select 2 neutral blue and red sets, and we need 2 independent forward computation chunks, and we need a matching point. 2 other things to mention here. First, in order to attack morons, we sometimes will partially solve the inverse of the permutation from the H-bit target to the matching point. Second, we sometimes set some conditions to control the propagation of the characteristics. We will see it in more details later. So the meet-in-the-middle episode is as follows. For all the values in the red neutral set, we compute forward to the matching points. And for all the values in the blue set, we also compute forward to the matching points. And we compute backward with the known H-bit target to the matching points to derive a filter. And then we filter the states. In the following, I will take Kachak as an example to show our automatic search model. Let's first look at it in a high level, and then we will go into details in each step. So according to the 3 configurations, we need to model the starting state, to model the attribute propagation, and to model the matching phase. And we also use some auxiliary techniques like setting conditions, and we use linear structure in the starting state, and we use the city kernel in the matching phase. Note that in the 5 steps in the round permutation in Kachak F, the row and pi only change the bit position, and the last step is constant addition. So we only need to consider the theta operation and the S-box operation. In our model, we use 5 colors to present each bit. The gray is constant, the red and blue is active, and the green is actually a linear expression of the red and the blue or gray bits. The white one is unknown bit. Since we have 5 colors, we use a 3-bit encoding scheme to represent them. Note that in previous work, there are only 4 colors, but in our model, we introduced green to represent the addition of the blue and the red bits, which can also be used in our model. In the starting state, each bit can take 1 color of gray, blue, or red, but we don't pick it randomly. Instead, we choose to follow the linear structure so that we can skip the first round for free. See, we set bits in this lane and this lane in the same color, and similarly for this lane and this lane. And we need to require the bit in this one, and the XOR of the bit in here and the bit here is constant. So after the theta operation, the color will not diffuse. And after the pi and the row and pi operation, the color will none of the two colors will be adjacent in the same row. Then in the next S-box operation, we choose to set more strict conditions to control the diffusion. So we set the right bit of the active bit be 0, and we set the left bit of the variable be 1, so that we can linearize the chi operation, so that we can skip it. Which means we can get the output of the first round by only considering the linear operation of the input. Then for the theta operation, we decompose it into 3 steps. First, in the first step, we consider the XOR of bits in the column. And in the second step, we consider the XOR of 2 columns. And the final step is the final result of theta operation. So the thing we need to do is to model the XOR operation with arbitrary number of inputs. Actually, we consider all the possible situations, and finally, we divide them into 5 classes. For example, if the inputs have unknown bits, then the output is unknown. It's simple. Or if the inputs have blue or gray bits, then the output can be blue without consuming degree of freedom, or it can be gray by consuming 1 degree of freedom of blue. We define 3 binary variables with 5 values to represent the 5 conditions of the input, and then we can give some inequalities to restrict the input and output to fulfill the 5 rules. And we also have some inequalities to constrain the degree of the freedom. Then for the chi operation, each bit bi is actually determined by 3 bits ai, ai plus 1, ai plus 2. Similarly, we also consider all the situations here. So for each situation, it actually corresponds to a point in a 12-dimensional space. Then we can derive the linear inequalities by computing the convex hull. To give a relation used in the matching phase, we here use the property of the chi operation, which is if we know 3 consecutive output bits, then we can give 2 linear equations of the input bits. So for Keccak 512, suppose the hash value is the first 512 bits of the in the R plus 1 round, then we can use such property to derive these 2 equations. What to do next is there is a trick here. We choose to add the same thing on both sides, so this equation still holds, right? So we get this ugly but very simple and useful equations. And then, according to the kernel property of theta, we can replace the XOR of theta value by the XOR of A value. So the equation will be transformed in a form in the following. Similarly for the second one. So please see what we get. What we get now is actually some linear relations of bits in the R round from the hash value in the R plus 1 round. So this equation can be used as a filter in the matching phase. But we need to note that the filter is valid only on some conditions. So these are the conditions on matching points. In order to find optimal attacks, we actually need to maximize the minimum value of degree of freedom of the red sets and the blue sets, and also the degree of matching points. We applied our techniques to Ketchak, Zodiac, and Escon. For Ketchak, we performed the attack with 2 message blocks, and we put the meet in the middle episode in the second message block. So the attack model involves too many states, so we divide it into 4 figures in our paper. Here is only one of them. I need to see that the degree of the freedom of the red set is 108, and the degree of the freedom of a blue set is 8. Sorry, there is a typo here. The degree of matching is 8. Here is the summary of the attack result of Ketchak 512. Note that our 4-round pre-image attack is actually better than the attack with rotational cryptanalysis. So our result actually breaks their nearly 10 years cryptanalysis records. And our technique is actually more generic. Note that previous pre-image attacks with the linear structure technique only arrived 3 rounds. And I don't have time to introduce the application of to Escon and Zodiac in this talk, but I put the summary of the attack results here. So for Zodiac, we give the first 3 round pre-image attack. And for Escon, we give the first 3 and 4 round pre-image attack. In the end, I will conclude this paper. So our work can be seen as the first attempt to apply the meet-in-the-middle attack on sponge-based hashing functions. With the MILP automatic search model, we give the improved pre-image attack on Ketchak, and we also give the first pre-image attack on 3-round Escon and 3-round Zodiac. Further work can be done in several directions. For example, we only consider Ketchak 512 in this paper, but you can also consider other instances. But I'm not sure whether the linear structure still works combined with the meet-in-the-middle attack. And we can also consider more tricks to with automatic MILP model to achieve non-negligible improvements. And since in our work it is a pre-image attack, we can also consider the clearing attacks or key recovery attacks. Actually, my co-authors have done something. They put the work on ePrint. Please refer to it if you are interested in it. Thank you very much for your attention.
Any questions for the speaker? Okay, so I have a quick question. Did you try maybe to apply your framework maybe to more reduced versions, but to have some practical results? Like maybe on a smaller pre-image target or fewer rounds, but some practical results?
You mean now or in the future?
No. Did you maybe try?
We haven't tried, but we can do it, I think.
Yeah, okay.
Okay, thank you very much.
Nice.
Thank you.
Okay, so if there are no further questions, then let's thank the speaker again.
Thank you.
Okay, so the second talk will be presenting a paper called Analysis of RIPE-MD 160, New Collision Attacks and Finding Characteristics with MILP. The paper is by Fukung Liu, Gaoli Wang, Santanu Sarkar, Ravi Anand, Willie Mayer, Ying-Shin Lee, and Takanori Zobi. And Fakung is going to give the talk.
So, thanks for the introduction. In this talk, I will introduce our work on RIPE-MD 160. It's a less popular hash function, and I also will try to solve a bit old problem, which is to find the differential characteristic for the MD-SHA hash family. So this is an overview of this talk. So let us start. RIPE-MD is a hash function belonging to the MD-SHA hash family invented by Dopkin et al. At FSC in 1996. The main purpose is to strengthen the security of MD5 because at their time, Dopkin has already showed a semi-free start cleaning for Furon MD5. So although it is less popular than MD5 and SHA-1, it has been used in practice, especially the Vietnam Bitcoin. So it's still very important, let alone it's also an ISO IEC standard. So we can imagine RIPE-MD, so I will simply say RIPE-MD instead of RIPE-MD 160. So RIPE-MD, we can view RIPE-MD as two parallel instances of MD5. But of course, in each single branch, they are indeed different from MD5 because you can, if we check, first, there are 80 steps there are 80 rounds, but in MD5 there are only 64 rounds. And if you also check the round function, you can also find that each internal state xi is updated with 5 consecutive internal states, while in MD5 it was updated in only 4 consecutive states. So the difference propagates in a much faster way in RIPE-MD. And due to the more complex round function, so it becomes more challenging to find valid signed differential characteristics. And due to the double branch structure, it's also difficult to find the conforming message pairs giving a specified differential chair. And it's also not easy to construct better local cleanings to increase the number of attacker rounds. So in this talk, I will mainly show how to find valid signed differential characteristics for RIPE-MD. So you may notice that I always emphasize the valid. So why the validity is so important? If you have any experience in analyzing MD-SHA hash family, you will know there is the differential characteristics. You should know that there are many bit conditions in it, and if you find this differential characteristic, you should be careful of the contradictions in these conditions. And in the case of RIPE-MD, there are 2 places the contradictions come from. The first place is the conditions imposed by the Boolean functions, and there is a very special place where another condition, which is the condition in Qi. So it's just like this equation, and where alpha I and beta I are constants derived from the differential chair. So let me give more details. Specifically, for many hash functions in the MD-SHA hash family, you will know each internal state xi will be used in 3 consecutive or even more steps in the Boolean functions. So, for example, xi will be used 3 times in 3 consecutive steps, and at each round, step round have the same meaning. At each round, there will be different conditions imposed on xi. So, finally, these conditions will be contradictory if we consider 3 consecutive rounds. And another place where contradictions occur is is the conditions on Qi. So you can see how Qi is computed. So Qi is computed with xi and xi minus 4. And if there are too many conditions on xi and xi minus 4, there will be only a few number of solutions of Qi satisfying equation 5. And what's worse, none of these solutions of Qi can satisfy equation 4. So this is where another place contradictions appear. So yeah, it seems very challenging to find the valid sign differential characteristic for FMD, but yeah, we indeed have mature and very powerful technique developed, I think, at Asia. Christine and Florian Mendel. So yeah, they did a lot of this work to continually improve this technique. So the main idea, according to my understanding, is just like shown in this figure. The first propagates the sign difference in two directions, and we call them the sparse part. And then we have to connect two sparse parts, and for the connection in the middle part, the differential characteristic will be very dense, and suddenly there will be many conditions. There will be many conditions to be added, so contradiction easily occurs. So we have to efficiently detect the contradictions at this phase, and this is what the guess and determine technique achieved. And if you have any experience to deduce such a sign differential characteristic needed by hand, you will know this is we indeed also do the same way. And connecting the sparse part is really a very painful process. I once done it when I was an undergraduate student, so many contradictions, so it's so painful, and I cannot find the valid one. So, but unfortunately, this is not open source, but we can still access these tools. They are very kind, and also collaborated some papers with some of these authors. But I want to have my own tool, and this is my personal interest. And we also know in recent years the MIT set SMT-based methods are very popular, but we have not seen its applications to this problem. And maybe we try a different approach, and there may be new potential. So let me highlight the difference between our method from previous works. So yeah, the last 3 points. First, we encode the sign difference transitions in the model for the first time. So indeed, in previous work, there exists set-based methods to solve this problem, but they only consider, the middle part, they only consider the model to describe two parallel value transitions. And we note that the value transitions are very expensive, so we remove this and we directly encode the sign difference transitions. But the contradictions easily occur. We have to efficiently detect the contradictions. So and one of the technique is proposed at Crypto 2020. So it's also one of my work. But this model is indeed very expensive, so we do not want the value transition. So we use a relatively light method. So we call it monitoring technique. I just want to use a name to distinguish from other works. And I strongly believe a similar idea has been used in the guess and determine techniques. Otherwise, we cannot find a valid differential characteristic. So how should we describe the target problem? Just like the cryptanalysis of block ciphers, what we need to do is to describe how the sign difference propagates through the round function of FMD, and this is a round function. So what we need to do is to construct to use constraints to describe the relations between the sign difference of di, I plus 1, I plus 2, I plus 3, I plus 4, I plus 5, and the sign difference of the message m. And if we consider the bit level, so this circular shift indeed only affects the order of variables, so we indeed can only consider a simpler form. So what we need to do is to find the relations between the sign difference between A0, A1, A2, A3, A4, A5, and the sign difference M. And if you have experience to deduce sign difference characteristics by hand, you will know what we usually do this. So we usually do this in this way. So first we consider the modular addition of the message and the constant, and then we consider the Boolean function, then we consider the sum of the B0 and B1, then we consider the sum of B2 and A0, then we consider B4, then we consider B5. So then we consider B1 equals to B5. Maybe you will think the last equation is meaningless, but it will be useful. And in other words, what we need to do is to introduce many intermediate variables to help trace the evolution of the sign differences. And note that this is the round constant, so we indeed do not need B0, and we can simply set the sign difference of B0 as the sign difference of AM. And again, if you have the experience to deduce such a characteristic by hand, you should know, what we usually do is like we first deterministically compute the sign difference transitions for the first, for this modular addition, this modular addition, and this modular addition. What does deterministic mean? It means, for example, we are given the sign difference of x and y, and we want to compute a sign difference of its modular sum. There are indeed many possible sign differences, but we only choose one because it is enough to carry the information that the modular difference of z equals to the modular difference of a and y. Then we need to deal with the Boolean function, and then we will get one possible value of the sign difference of B5. Then, so what we do, many steps are deterministic, but what we need is the sign difference of A5. So we will expand this sign difference to get the sign difference of A5. So maybe you will get confused if you're not familiar with this direction. So if we carefully analyze what we usually do by hand, we will know we need to deal with these three problems. So the first problem is how to compute a unique sign difference to capture the propagation of the modular difference through the modular addition. And the second one is how to model the sign difference propagate through the Boolean function. And the second one is the last step, how to expand a sign difference so that we can get many possible sign difference such that their modular difference are same. So in sign difference, there are three states. NU equal, where N means the bit is changed from 0 to 1, and U means the bit is changed from 1 to 0, and equal means, there's no change. So we indeed tried several methods to describe these three states, but we finally found that it's better to use two binary variables, but we also restrict that these two binary variables can only take values from this set. So because 0, 0, and 1, 1 indeed carry the same information, which means there is no difference in this bit. Then let me slightly go through how we did it. So it's indeed quite simple if we know how to have this big picture in our mind. So we just need to proceed the sign difference transitions bit by bit, and what we need to do is to give the propagation rules for the sign difference transitions. And according to our description for the sign difference, we can simply convert the propagation rules into a choose table for the variables describing the sign difference, and then we can again use the software logic Friday to get the equivalent linear inequalities describing the choose table. And so this is the linear inequality system. So where the coefficients, this is we can simply get such a matrix. And similarly, as for how to model the expansion of the sign difference, note that what we need to do is to get all possible sign difference from a given sign difference such that their modular difference are same. So again, we can do this so with some propagation rules. And it's indeed, we can indeed interpret this as traversing a tree. It's indeed like a tree structure. For example, here there are branches, but there is no branch. If we check this propagation rule, you will see no branches. So and for the Boolean function, again, very simple. We get the propagation rules for these bits, and we get the choose table, and we get the linear inequality systems. Again, so it's done. And but we have not yet considered the contradictions in the conditions, how to do it. So first we need to deal with the contradictions in the Boolean functions. So we simply introduce x, y, z representing the values into the model. So here, this means the sign difference, but this means the value. And we construct a much larger table to describe all valid tuples, all valid values of this tuple. It's a bit long, but it's useful to detect the contradictions in the Boolean function. But not yet over because we still have contradictions in the Q. So this is indeed a bit involving, and you have to refer to one of my paper at Eurocrypt 2017. And we finally found that these three equations are sufficient to detect the contradictions in it. So indeed, this is not a very easy problem. There are many other minor details, and so I cannot introduce all of them in this short presentation. And I also, to increase the flexibility of our model, we also have many optional parameters to control the searching strategies in our model. So you can check it out. And we apply this to RapMD and get some new attacks on 36 rounds. But a question quickly arises, which is this technique really useful and efficient because we have the powerful guess and determine technique? Can it really beat this technique? We did not answer this question in this paper, but in our follow-up paper, my colleague Yinxin did some amazing work, and he showed, this method can indeed beat the guess and determine technique in some sense by giving the first semi-free start cleans for 39 rounds SHA-256. And this updates the best record kept by Mendel after 10 years because they cannot find such a differential chair. In summary, we propose an alternative method to find sign differential characteristics for the MD-SHA hash family. This is very new, and it's the first attempt. Maybe we can improve its efficiency with some other strategies, and I hope there can be more applications of this technique. For example, SHA-2 is very important and is used worldwide, so we should target. And the code is also open source. So thank you. Thank you.
Any questions for the speaker? So just a quick question. Maybe I missed it. What is the complexity of the attack, roughly?
For our attack, for the 36 round, the time complex is 2 to the 64. But now we have updated that by giving the first practical clean for 40 rounds.
Okay.
So it's done by Yinxin, so it did.
Very nice.
Very nice.
Okay, so let's thank the speaker again. So the final paper in the session is called Collision Attacks on Round-Reduced SHA-3 using Conditional Internal Differentials. And the paper is by Zhongyi Zhang, Chenggan Hu, and Micheng Liu. And Zhongyi is going to give the talk.
Okay, thanks for the introduction. Good morning, everyone. I'm Zhongyi Zhang from Institute of Information Engineering, Chinese Academy of Sciences. It's a great pleasure to be here with you. My topic is collision attacks on round-reduced SHA-3 using conditional internal differentials. This work was done together with Chengyan Hu and my supervisor, Micheng Liu. My talk will be divided into these aspects. Let's start with the background of hash function and Q-check, and the previous work, and also our contribution. Hash function is a simply mathematical algorithm that maps an arbitrary length input to a fixed length debit output. In cryptography domain, hash function should satisfy several security properties. One of them is collision resistance, which is that it should be hard to find two messages that are distinct, M and M prime, such that these two messages through the contribution of hash function will lead to the same output. In our work, we focus on collision attack. This is a short introduction of Q-check. After MD5 and SHA-1 was written, NIST opened the SHA-3 hash function competition in 2007. And the Q-check was submitted to SHA-3 competition in 2008. Its designers are Bertoni, Diamond, Peters, and Asha. After 4 years, Q-check became the winner. And in 2015, it was standardized by NIST as SHA-3. SHA-3 has 6 versions, including 4 hash functions and 2 extendable output functions. Q-check adopted sponge construction. Sponge construction as a framework for constructing a hash function from permutation. It utilizes Bay-bit underlying permutation Q-check F. F contains 24 rounds. There are 2 parameters, bit rate R and complexity C. The sum of R and C is B. Q-check takes in a message and output a Bay-bit digest. So before processing, the message is printed and then spelled into R-bit blocks. Each block is exported to the first R-bit and before applying F. Q-check has an internal state of 1,600 bits, which can be seen as a 5 × 5 matrix, where each cell is a 64-bit line in the direction of the z-axis. Its run function R consists of 5 steps: set, row, pi, chi, and alpha. And the first 3 steps is defined by L, the linear layer. Chi is the only nonlinear operation. The figure on the right shows some notions determined by the designers. Okay, this is the run function of Q-check. In int step, int add 1 round-dependent constant to the first line to destroy the symmetry. It can't be ignored in internal differential cryptanalysis. Now let's see the previous work and our contribution. We utilize internal differential cryptanalysis, which was developed by Thomas Perrin in Crypto 2010 and generalized by Dina, Dinkelman, Shamir in the analysis of Q-check. In the paper of FSE 2013, Dina et al. Mainly utilized these techniques such as squeeze attack, internal differential characteristic, target internal difference algorithms, and the proposed practical attack on 3-round Kerchak 384 and 3-round Kerchak 512, and also proposed theoretical attack on 5-round Kerchak 256 and 4-round Kerchak 384. The major contribution in our work is that we utilize a conditional internal difference to propose collision attacks on up to 5 rounds of 6 SHA-3 versions. In particular, for 4-round SHA-3 512 and 5-round SHA 256, the complexity achieved to 237 and to 185. Okay, the second part is an overview of the attack. During our study on internal differential cryptanalysis, we found that it can be viewed as a variant of burst attack. For the general burst attack, assume that the hash function H maps one input subset to one output subset D of size 2 to the power of n. So to find the collision, we need about 2 to the power of half of n inputs from S. For a variant of burst attack, assume a hash function H maps input subset S to multiple output subsets D1, D2, until D2 to the power of k, which are called collision subsets, and the size of each dj is 2 to the power of m. So to find a collision, we need about 2 to the power of half of m plus key inputs from S. For this type of attack, we can perform parallel research on multiple subsets di. Since the size of each di is similar than d, we need similar hash table size. Okay, let's briefly introduce the internal differential cryptanalysis. For standard differential cryptanalysis, we consider message pairs which make up a pair of states, and we consider the evolution of difference between the two states. However, in internal differential cryptanalysis, we have only one single state and divide it in 2 parts. We are tracking the difference between the 2 parts of a single state. For generalized internal differential cryptanalysis, we consider more complexity differential relations between multiple parts of a single state and consider their evolution. For conditional internal differential cryptanalysis, we can find messages conforming 2-round internal differential characteristic by adding linear conditions to the initial state space. Okay, let's see a special type of states which could be called symmetric states. If one state has carried I in the axis, as shown the following formula, it is called a symmetric state. Since the fundamental period corresponding to I is the greatest common divisor of I and 64, I can attain non-trivial values. Here is an example for a symmetric state with I equal to 16. Okay, this is a property of symmetric states in Kerchak, which is that symmetric states will maintain symmetric after applying the first 4 operations of Kerchak. If we start with a symmetric state and apply any of the first 4 step mappings, we will end up with another symmetric state. Okay, let's introduce the internal difference sets. Given a period I, the set by adding a single representative state V to all symmetric states is an internal difference set, which is called internal difference for short. If V is a zero vector, the difference is zero. The internal difference is zero internal difference, which is exactly the set of all symmetric states with period I. Finally, similar to the case of question groups, the action of linear mapping on any internal difference is equivalent to acting on the representative state. Okay, let's see the framework of the attack. For 4-round collation attack on chassis, what first we do is selecting message M in the initial internal difference such that the state enters the internal difference of the second round in a given characteristic, then calculate the internal difference of M after 3 rounds of round function and store the state into a subset. Finally, calculate the collation subset of each subset of I with JSV in turn until one collation is found. For 5-round collation attack, we choose 2 block messages and employed target internal difference algorithms, TIDA, to complete the first step. And in the following 2 steps, we just add an extra iteration of round functions, and the framework is similar to the 4-round collation attack. Next, we will introduce the basic techniques of these 3 problems. This is the third part. First, how to estimate transition probability of internal difference. Let's introduce the differential transition conditions. Given the input difference start in of Q-check S-box, the output difference start out is determined by Q linear conditions, which is denoted as differential transition conditions. The delta out is represented by the following formula, which ensures the correctness of definition above. We also defined the difference conditions table, DCT, and the values of difference conditions table, VDCT, based on the differential transition conditions. Now we can estimate the transition probability of internal difference. The rank of linear equation system E, composed of all differential transition conditions of an internal difference, is the transition condition number. The transition probability is lower bounded by 2 to the power of negative k, where k is the transition condition number. Okay, next we will introduce how to find messages conforming to round internal differential characteristic. After giving an internal differential characteristic, assume that the symmetric states of each internal difference are x, y, z, w respectively. So our goal is to find x such that y and w satisfy the respective differential transition conditions E0 and E1. Finding y is easy because y can be represented by Lx. We just need to submit it into E0 and solve it for x. For E1, we should linearize each zi in E1 such that E1w is a linear equation system in X. Okay, finally, we will introduce the target internal difference algorithm. TIDA. The target difference algorithm was introduced by Leiner, Dunkelman, and Shamir, and developed it into TIDA in the analysis of Kerchak. In our work, we separate the difference phase and the value phase, and we reduce the number of iterations for the two phases. Okay, after solving the three problems, combining with a given internal differential characteristic, we can obtain our results. This is the last part. Here are the attack results and the internal differential characteristics parameters we used. We can find that the small period I will lead to small complexity and also reduce the degree of freedom. We first need to ensure there are enough degrees of freedom to generate at least collision. Okay, this is a summary and future work. In this paper, we utilize conditional internal differential to find collisions for up to 5 rounds of all SHA-3 functions. And we proposed the first collision attacks on 4 round and 5 round SHA-256, and achieve the best collision attack on 4 round SHA-3 512. For the future work, an interesting work is to find better internal differential characteristic. Another work is apply internal differential analysis to other ciphers. Okay, that concludes my presentation. Thank you for your attention.
Any questions? Can you please approach the microphone?
Yeah, cool. So just to clear it up, because I don't exactly have a background in differential cryptanalysis, so I was a bit confused. But so you mentioned use of different different condition tables, right?
Yes, these difference conditions table.
Yeah.
Yes.
So previously we heard about difference distribution tables in one of the previous talks yesterday. Are these the same things with different names, or is there a difference between the two?
Sorry,
So basically, a difference distribution table basically tells you, given a characteristic, what's the probability of a transition happening. So is it the same thing here, or is it slightly different? How does this work?
Sorry, I don't know the difference between them.
Okay, no worries.
Maybe we can communicate after reporting.
Sure. Okay, sure. No worries.
Thanks.
No worries.
Any more questions? Okay, so if not, then let's take the speaker and all the speakers of the session. So I think we now have a coffee break.